Alright, so Hamish, which one was this now?
Number one. Actually, if I knew one, I could do the rest.
You think so?
Yes, because I just need to know how to start the menu.
Yeah. Alright, soon. The questions that you had trouble with were just the questions of the explanation, right? Or is it?
I haven't finished. So
Yeah.
I mean, for anti-bands, I haven't finished, but anti-5, I finished except the explanation.
The explanation ones, yeah. So, Turners, you feel that you just need to see number 1 and you think you'll be okay?
Yeah, 1A.
1A, okay. Yeah.
1B and all the question 5.
Yeah, okay.
Yeah.
Okay, I'll tell you what. What I'll do is I'll do all of number 1 now, and then we can give some time later to more of these, because remember I said later in the class you can work on the rest of the questions, okay? Yeah. No. Is it a calculation or an explanation? Anyways, I'll tell you what, we'll just look at number 1 now, and then we can have a look at that one later, okay? So can you all have a look at number 1 on page 80? Okay. Right. So we'll just, write a short account of simple harmonic motion, explain the terms amplitude, time, period, and frequency. Alright, just really quickly, what's amplitude? Maximum displacement. Time period? Time taken to complete one cycle, yeah. And frequency? Amount of cycles per second. Yeah. A particle of mass m moves such that its displacement from equilibrium position is given by y equals a sine omega t. Come on, Mo. Now notice, hey guys, notice I use capital A instead of small a in the question. Why do you think I did that?
To differentiate acceleration from...
Yeah. Where A and omega are constants. Derive an expression for kinetic energy of the particle at time t and show that its value is a maximum as the particle passes through the equilibrium position. Okay. So what I'll do is I'll just get rid of that here. They use the letter Y, but I'll just use the letter X. Now, you remember I gave you these formulas yesterday, didn't I? So, if X is the position, what one would be the velocity? It'd be A omega cos omega t. Yeah? You remember that from yesterday, don't you? Yeah? Now, well, we start with sines, the next one, they always alternate, so it must go sine, cos, sine. Yeah. What's the formula for kinetic energy? A half mv squared. So, in this case, it'd be a half m a squared omega squared cos squared omega t. Yeah. Now, they want the maximum kinetic energy. So what is the biggest number cos can be? Yeah, cos. Cos can be 1. And the smallest? 0. So here, the kinetic energy, the maximum would be a half m a squared omega squared. That's the maximum it can be. And what's the minimum it can be? It could be 0. Yeah? So I think that's what they want, isn't it? Find an expression for the kinetic energy and then the maximum kinetic energy. Yeah? I mean, that's it then. Okay, next part. A steel strip clamped at one end vibrates with frequency of 30 Hertz and amplitude of 4 millimeters. Okay, can I scroll down? Yeah. Alright, what's the frequency? 30. And then the amplitude? 4 millimeters. So that's 10 to the power minus 3. Okay. Now what do they want? They want the velocity. So we can use the formula we actually had earlier. But before I use that, I should probably find what the omega is and the t. So we have t equals 2 pi over omega, and all t equals 1 over f. That's the other one as well. Okay, so then what is the t here? It's 1 over 30, isn't it? And I can put that in there. I get omega is 2 pi over t. So what's omega? 2 pi over 1 over 30, yeah. So that's 60 pi. That's the omega. Now, what do they want? They want the velocity. So you had the formula a moment ago. What was the velocity formula? V equals A omega cos omega t. The velocity of the free end as it passes through the equilibrium position. Okay. So in other words, the velocity at the beginning. So, yeah. Now how did I know that? Yeah, the equilibrium is the origin. And if this one uses cos, what one did x use? Sine. And when do you use sine? No, that's cos. Sine is when it starts at the equilibrium point. Yeah? Yeah. So this one starts at the equilibrium. So what should I put as the value for t if I want the velocity at the equilibrium? No, 0. Yeah? You seem confused. Yeah. Listen. Yesterday, remember we had two possibilities, sine and cos. Yeah. So when do we use, or which one do we use when it starts at the end? Cos. And when it starts at the middle? Sine. Okay. So if it's sine and cos, then the velocities will be the other way around. Remember? So if we use cos, then what do we use for the velocity? Sine. And if we use sine, what do we use for the velocity? Cos. Now what am I using for the velocity here? Cos. So what was the original? Sine. So is that the middle or the end? The middle. So it starts at the middle. Yes? And they want the velocity at the middle. So in other words, they want the velocity at the start. Yes? So what should I put for t? The time. Yes? You get the answer if you put t as 0. As 0 or as, what do you mean as nothing?
Because t cancels out omega and I'm only got 30 omega.
Ah, you put t as 1 over 30, was it? Yeah. So you put t equal to big T, which means, what does big T mean? That's the time it takes to do one cycle, isn't it? So when you put t equal to this number, you're finding the time after one cycle. If it starts at the beginning, where will it be after one cycle? At the beginning. Yeah, so that's why you got the same answer. Yeah, so that's fine also. So if I put t as 0, what's cos 0? 1. So I'm just left with a omega. And we have a and we have omega. What was a?
65.
No, yeah.
4 meters is 4 times 10
Yeah, and then omega was 60 pi. Okay, what does this equal?
So could you repeat why is the t 0?
Yes. It starts at the beginning. Or is that part unclear?
0.75.
Yeah, that's the one.
Okay, alright. 1 second, yeah?
0.75 meters per second.
0.75 meters per second. Okay.
Because I subbed 1 over 13 to the t, and that's when I got the mistake.
Oh yeah, but that's the exact same thing that you did.
Yeah.
Except did you use cos or sine for FV?
Cos.
You used cos?
Yes.
And you used t as 1 over 30?
Yeah.
And you used omega is 60 pi? They should have gotten the right answer. Do you want to just double check it? Joshua, that's what you typed in. You typed in the exact same thing as Tanish, yeah? And you got the same answer. Is your calculator in radian mode? Your calculator's in the wrong mode. It should be in radian mode, not degree mode. Remember radian mode? Yeah. Do you know how to change it?
No.
Okay, that's the problem then. Shift mode and then pick radians. Now type it in again, you get the right answer. Yes? Alright, next. The acceleration. Okay. So what's the formula for acceleration if that's the formula for velocity?
A squared.
Yeah, A omega squared sine omega t. Oh, sorry. Well, why did you say cos? It doesn't matter. No, we can use sine. Yeah, it doesn't matter because they want the maximum. Yeah. So what's the maximum sine can be?
0 to 1.
And what's the maximum cos can be?
1.
So it actually didn't matter which one to use. So A maximum is equal to A omega squared. So again, type in the numbers. 4 times 10 to the minus 3 times 3,600 times pi squared. Okay. 1.4 times 10 to the 4 meters per second squared. Did you get the same answer?
Yeah.
Yeah? Soon? Yeah. Okay, we'll spend more time on this later today, maybe. Okay? But I think the only problem really was just the mode on the calculator, that was all. You used the same formulas as me, did you?
Yes.
Yeah, so there's no problem then. Yeah. Okay, we'll go on to the next chapter then. But we'll spend more time on this later. Okay. So can you go to page 82 now?
Like, it doesn't matter like if I got the same final answer with numbers for.
Yeah,
Yeah.
it's fine, yeah. Yeah. Okay. Yeah, page 82 then? Yeah. Yep, okay. Right. Now, I think I told you this idea a couple of weeks ago. Yeah, you remember it? What's conservation of energy? That's it, yeah. That energy cannot be created or destroyed, but just changes form. And that is definitely the most important rule in physics. Okay? That is the most important law in physics, that you cannot create or destroy energy, you just change its form. So, just to point out, although we don't have to worry about it, you see on page 82, you see all the different units there, up the top, table 10.1. You see that there? Yeah.
Is this also one of the laws for thermodynamics?
It is, yeah. Which one?
The conservation of
Oh yeah, which number though?
2.
Yeah.
Weird.
1. Yeah. And we'll do a little bit of that in semester 2. You see table 10.1?
Yeah.
What units do we have? We have joules, kilowatt hours, term, and BTU. Yeah, now see, these are units that they use in the UK. Alright, but we don't need to worry about that in the exam, because in the exam we use which unit for energy? Joules, or kilojoules, okay? But there is another unit which we can sometimes use, okay? Yeah, and it's actually the next one there, kilowatt hours. I just need to talk a little bit about that. Kilowatt hours. Okay, well, we can kind of almost work this out. What does kilo mean? How big is kilo? 1,000. So it's 1,000. And watt is... Yeah, but what is the other unit for it? 1 watt is... How big is 1 watt? so many, how many joules?
365.
No. 1 watt is how many joules per second? Oh, I forgot. 1 joule per second, isn't it? Yes. 1 watt is 1 joule per second. So this here is 1 joule per second. And an hour is how many seconds? 3,600 seconds. What happens to the seconds? They cancel, don't they? So they cancel, and you're left with 3600,000 joules. Okay? 1, 2, 3, 4. Okay, so if you want, you could say 3.6 megajoules. That's 1 kilowatt hour. Now, why is this unit important? Where might you see this unit? Does anyone know? Yes. Yeah. Where else? Yeah? Where was your bills? Yeah. Yeah. When you get your electricity bill, they charge you per kilowatt hour. They don't do it per joule because you can see it's too big. So if, for example, you get your electricity bill and they say you used 50 kilowatt hours, well, how many joules would that be? That would be 50 times 3.6 times 10 to the 6. Yeah. What's that? Can you type it in? 180? 180? Megajoules, yeah. 180 times 10 to the 6 joules. Yes. So they don't charge you per joule, they charge you per kilowatt hour, which is about, well, it's exactly 3.6 million joules. Okay? So that's the first thing. Right, okay. Next now.
Do we always use 10 to the power 6?
Yeah, or you can write megajoules if you want. Yeah. Just before I continue, I want to put this number, try and give you some scale of how big this is, okay? 1 kilowatt hour. So, how big do you think those light bulbs are? What power do you think they are? One of those, well, there's actually 4 of them there. How many watts? Light bulbs are usually watts, aren't they? Yeah. Maybe each one is 50, yeah? So if I have 4 of them there, 200. And let's, how long do you think it'll be on for today in this room? How many hours? 6 or 7 hours, yeah? So let's work that out. It's 200 watts times, we'll say 7 hours. How many is that? That's 1400 watts. Yeah. Yes, it's over 1 day, isn't it? Let me just get rid of the units for a moment. So it's 200 watts times 7 hours. But we shouldn't really use hours, we should use seconds, shouldn't we? So we should do 7 times 60 then. Yeah?
Times 360.
Sorry, and another 60, yes. So what's that in total?
25,200.
25,200 joules.
No, times
So I said it again? Oh, no, there's
2. Okay, 50.
Yeah.
504.
504.
Actually, it's 5,040,000.
Yeah, 5 million.
Yeah.
4.
So we'll just say roughly 5 million?
Yeah.
Yes, okay. So roughly 5 million joules. Need another 0, don't I? Roughly 5 million joules. How many kilowatt hours is that?
We'll compare it. We'll make it times 3.6.
Yeah, well, just divide it by 3.6 times 10 to the 6. So how big is that? 18.1.
I got
1.81. Thank you. 1.4.
1.4. Exactly, because identity is like 5 million.
Okay, alright, 1.4. Yeah, so our electricity company will charge us 1.4 kilowatt hours. Does anybody know how much 1 kilowatt hour would cost you? The price? Here, yes, here, yes. It depends, but do you know off your electricity bill? No. Yeah, maybe about 25 cents.
Is that cheap?
It's not, you see, you think it's cheap, but it's not actually. It's about 25 cents. So they charge you 25 cents. So, that's not too much. How much would that be now? About 35 cents? About?
That would be.
Yeah, 55.
Yes.
Yeah.
About 35 cents. Now you might think, oh, that doesn't sound much because that's for the whole day.
But it's only one room.
Yeah, but it's only one light in one room.
How many rooms?
How many rooms? And in fact, lights don't use that much power. What electrical appliance uses the most power in your home? Iron. No, fridge actually doesn't use that much.
Yeah,
Did you say air conditioning? Yeah, we don't have any of that here. Yes. Here. Electric heater if you have an electric heater, but I think there's something bigger than an electric heater. Iron's not too bad. Immersion would use a lot, yeah. We're thinking along the right lines now. Dryer would also use a lot, but I can think of something bigger. It would be two things. Electric kettle would use a lot, but the thing that would use the most would be an electric shower. Electric shower, yeah. Now, when I say electric shower, I mean a shower where the water is heated by electricity. Okay? I don't mean a power shower. I mean a shower where the water is heated by the electricity, not by a gas boiler. Yeah. Now, a lot of homes will have gas boilers.
There's still like they have that.
Yeah, you're using an electric shower because there's always a temperature. There's a temperature dial on it, and then there's usually sometimes two buttons. So you press one button if you want half the heater on, and both buttons if you want both heaters on. But I think if you just have a shower that's heated by a gas boiler, they'll have the temperature, but they don't usually have these two buttons. It's usually a bit different.
Well, if you don't have that, you just have to
If it's just a dial,
Yeah.
it's probably just a gas boiler. It's not electric then. So if you have an electric shower, light bulb we said is about 200 watts. Would anybody want to guess what an electric shower might be? So light bulb is about 200 watts. 1,000 watts? Yeah, I think it could be 20,000. Yeah. So you see it's much bigger than having the light bulb on. Yeah. So your light bulb costs you 35 cents, alright? And you think that's not bad, but light bulb is quite low. Everything else in the house is much higher than a light bulb. Okay, so that is expensive. Yeah. Okay. So we're talking about home, so I need to also talk about efficiency. Can I scroll down? Yeah. Okay, so we have a formula here. This is the symbol for efficiency. Does anyone know this word, efficiency?
Yes.
Yeah, what does it mean?
It's the best way to.
Best way to do something, yeah.
Yeah.
What else?
That's
Yeah.
Like in terms of energy, it's the best way to preserve or keep using energy without
That's it, yeah.
running out of the supply for it.
Yeah, that's it. And then you also gave it as a formula as well. What do you think it is? Yeah. Efficiency is the output over the input. Multiply 100%. That's efficiency. So we'll do an example of using this formula, and we'll pick something in the house again.
Solar panels.
We'll get to those, don't worry. So we'll go back to our light bulb. Oh, I should also point out, by the way, guys, here you can use either watts or joules. Okay? So the unit here is not too important. You can use watts or joules. Why is the unit not important? Because the unit will be the same on the top and the bottom. And then what would happen to the units? They cancel. So it's not too important. We can use watts or joules. It's okay. Now, we go back to our light bulb. So how much energy, or what's the power of our light bulb, we said? What number did we choose? How big did we say? 200. So is that the input or the output?
Input.
It's the input. It's how much the electric company charges you. It's how much you used. Okay. So it's 200. Okay, so just to be clear, right? There are 200 watts going into that light bulb. Now remember, what did I say at the start of the class? What's the rule at the start of the class, the law? Conservation of energy. So that 200 watts gets changed into different energy. What energy does it get changed into? Heat and light. Which energy do we want, the heat or the light? Light. So 200 go in. How much do you think gets changed into light?
150.
How many watts? Give me how many watts?
160 watts.
60 watts, you think?
160.
160? Oh, that's way too small.
I do like both having 360.
Yeah, so you think, for example, 200 go in and 70 come out? Yeah? Try smaller. Yeah?
70.
60.
Smaller than 60?
40 watts.
Smaller than 40?
10 watts.
We're getting closer now.
5 watts.
I think about 5. Yeah, so 200 watts go in, and how much comes out as light? 5.
So 2.5.
5, okay? So yeah, if you put 5 in there, get me the efficiency here.
2.5.
Small, isn't it?
2.5.
2.5.
Yeah, 2.5. Oh, by the way, don't type the percent symbol on your calculator, okay? Just type the numbers. 2.5%. So where has most of this energy gone?
That's the heat.
As heat. Yeah? Terrible, isn't it? Yeah? We need to use lights a lot, yeah? Yes.
So is the input same as the velocity ratio?
Is the input same as what?
Velocity ratio.
What do you mean by that though? Velocity?
That's about mechanical advantage and
Yeah. Yes, okay. We actually, we don't do that form of mechanical advantage. So this is where you have levers, isn't it? And things like this. Yeah. And it is the same idea, but it's not the same formula. But it's the same idea, mechanical advantage. Yeah. Now for our course, we just use efficiency when we talk about power and energy, not with mechanics so much. But I know what you're talking about, like you're pushing something up a ramp or the lever or something. Yeah. No, we don't worry about that one. We just use this one here. Okay. Right, so that's 2.5%. Lots of it losses heat. What do you think in your home is near 100% efficient?
As in doesn't lose any energy?
Yeah. That is as near to 100% as you could really be. No, I think we can do better than electric kettle, because if you think about electric kettle, the outside of it gets really hot, doesn't it? Like you can't touch it, so lots of heat is leaving.
So microwave?
Vacuum. Microwave would be pretty good. I think we could do better.
Oven?
No, because if you think about it, you can feel the heat coming out of the oven sometimes. No.
TV?
How about
No.
heater?
Yes, you're exactly right. Electric heater, because it's only heat. So if it lost energy because of heat, it didn't really lose energy, because that's exactly what you want.
Radiator.
Yeah, the electric ones though.
Yeah.
So electric heaters are nearly 100% efficient. No, the electric ones, the ones you plug in.
In terms of the energy.
In terms of the energy you put in, nearly equals the energy you get out. So they're nearly 100% efficient. Yeah. But there is some energy loss though. tiny amount. So how would the energy be lost in the electric heater?
Light.
No? So it doesn't all come out as heat though. Some energy is lost.
Light.
Yeah. You know, some electric heaters, they glow, don't they? But let's not talk about those ones. Let's talk about the ones that don't glow. That look like this. No? Well, a little bit will be lost to sound. Yeah, because you can hear when an electric heater's on. Can't you? Yeah. So this is how it's not nearly 100%. Do you think it's possible to get 100%? No. Yeah, but these things never really happen. So you can never get 100%. And what about more than 100%? No. Because what would happen if it was more than 100%? Not explode. No. Yeah. What do you think more than 100% means?
It's like
More than
create,
Yeah, more than the input, yeah.
create like another.
Create more energy than what you put in.
Which breaks them.
Yes, it certainly does. So it must be less than 100, okay? I wouldn't say it can be equal 100. In fact, I would say it's impossible. Okay? So can you make note of that? That's important to know. So if you're curious, if you look at the bottom of page 83, there's a table there that shows you how efficient different things are. So in that example, what do they have as most efficient?
Large electric.
A large electric motor. And car engine, how efficient is that?
It's low. So
Yeah, it's only 25%, isn't it?
yeah.
So if you think about it, that means every time you put 4 litres of petrol in your car, only 1 litre is being used to get you where you're going. And the other 3 litres you paid for, what happened to that?
Gas.
Gas coming out the back, sound, what else? A big one now? Heat, yeah, from the engine. Alright, so you pay for 4 litres, you only get 1. Yeah, it's not great, is it? Okay, can you go to the next page now, 84. Okay, so just as a small exercise just before we get started, I would like everybody to write down as many different forms of energy they can think of. Okay, so for example, we have done 2 forms already. What 2 have we done? Kinetic and potential. And we were talking about one today, electric. Yeah, so I want to see how many you can think of. So make me a list of all the different forms of energy you can think of.
Even hypothetical.
Let's just keep it proven, okay? So just real ones. Okay. All right, shall we hear what people have? Yeah? 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 All right, so let's start then. So kinetic, potential,
Thermal.
Chemical.
thermal, yeah, or in other words, heat. Heat, yeah. What else?
Solar.
Solar, which means light. Yeah.
Nuclear.
Nuclear, sound,
Wind.
wind,
Water.
which is really just like kinetic.
Water. Hydrogen.
Yeah, but again, that's like, it's like potential, because it's usually in a dam stored up high. What else? No. Chemical. Yeah,
They're mechanical.
that's more like kinetic and potential. Electrical. Yeah. Sound, light. Yeah. Good. Okay. Yes. Yeah. This type electromagnetic. Yeah. Yeah. But that's much more complicated. Yeah. Now the reason I'm talking about this is because in the exam they'll often ask you a question like, "It is not 100% efficient. Where did the energy go?" You see? So in my example of the light, where did the energy go? Into heat. But in the electric heater, where did the energy go? Into sound. Okay? So it's important that you have this vocabulary so that you can make an explanation. Now, they often just want like one sentence. You know, you could say something like, the energy was converted into heat. Or the missing energy was converted into sound. That's all they're looking for. Yeah? Is that okay? Yeah. Now, do you think it's possible to change any one of those into any other form? It is possible. Yeah. And we'll just talk a little bit about power stations. So power stations, what type of energy comes out? Electrical. But what type goes in?
Nuclear.
Yeah, well that's one possibility, isn't it?
Yeah.
But let's try and stick to Ireland for the moment. So what? We don't have nuclear in Ireland, so... Hydro, which is... Yeah, but what type of energy is that then? Not kinetic and potential. So you know there are hydropower plants. I'll try and draw one.
Also wind.
Yeah, we have wind as well. So what happens is you have the water stored here. What form is the energy when the water's up the top? Potential. And then the water flows down. And then what is it down at the ground? Kinetic energy. Yeah. And then it goes into the power station. Now, we'll talk about this when we do electricity after the break. But you have these big turbines. Very good, yeah. And these spin around. And then what happens when they spin around? They make the electricity, yeah. So they change kinetic into electrical energy. It doesn't. You see, it'll just be dumped into a river or something. So, yeah, so what would happen is this would need to be by a waterfall or something. So what would happen is the water, goes into the river, then, when it's hot, turns into vapor, goes back into clouds, rains down. The water cycle. We don't have to worry about that. Yeah. So it goes potential, kinetic, then electric. So that's how you can change potential and kinetic. But what are the other types? So not nuclear. What else do we have in Ireland? Chemical. So how do chemical power plants work?
Burning fossil fuel.
Yeah, so how does that make energy? What do you do there?
The heat comes
Yeah, so you burn your fossil fuel and it makes heat.
Yeah.
But what do you do with the heat? So you have heat energy here.
Have a way of trapping the heat and then
Yeah, but that's my question. How can you do that? Yeah? Any ideas? How to get the energy from the heat to do something useful? No? Okay, that's okay. So what you do is you heat... Yes, you heat water. Then what happens to the water? Boils, turns into steam.
yeah.
So then what do you do with the steam? Yeah, you push it down a pipe. And then what does it do then? Again, it turns the big turbine.
Steam.
Yeah, the steam. Yeah. Yeah. It's exactly the same with a train. An old train. Locomotive, yeah. Coal burns, and the coal changes the water into steam, and then the steam pushes the wheels around. So, what form is the energy here? Chemical. And then here, heat. And then here, kinetic. It turns the wheel, and then out comes electric again. Okay?
Isn't it wind?
And wind. And the last one we'll do is wind. So, I think that's the easiest one as an idea. Yeah? Okay, we'll do solar as well then. Wind and solar, they're not too long. So how does wind work for making power? Yeah, it's the simplest one, isn't it? The The wind just turns a wheel, which turns the turbine, so out comes the electricity. Simple as that. And then the last one then, solar. Yeah, now this is something that we'll have to do in the last part of the course, okay? So we won't talk about how it does it now, but the light hits a special metal surface, and the metal surface sends the electricity, it frees the electrons, okay? But we won't talk about that now. Frees the electrons. Yeah, so when the light hits the metal, the electrons are free and they move.
Sort of like photosynthesis.
Yeah, it's a mechanical version. Yeah. Thermal is the same really as the chemical one I did. It's turning heat. So, some places they have the heat under the ground. Places like Iceland, I think, maybe. They have lots of the hot steam under the ground. Geothermal, very good, yeah. So what do they do here? Well, they just connect directly to the source and let the steam up through the pipe. It can turn the turbines like this.
The metal plate for this one, is it thermionic condition that releases the electricity?
Yeah. The light photon hits the metal plate and releases the electron. But this is something we'll talk about in the last part of the course. Okay. So which one of these methods is the best method?
Solar.
Yeah.
Solar.
Yeah. Well. Yeah. No. She makes a good point. It depends on the country, doesn't it? So I don't think solar would be so successful, right?
Back home.
But back home it would be. Yeah. So what do you think would be good here for Ireland then?
Wind.
The wind. Yeah. On the west coast of Ireland, there's lots of wind energy coming in from the ocean. Okay. In fact, the west coast of Ireland is number 3 in the world for most wind energy. There's only 2 other places in the world that get more wind energy on the coast. I'm not sure which 2. No, I don't even think it's the UK. I think it's more than the UK. I'm not sure. I'll have to check. I know that Ireland's west coast is number 3. So in other words, wind in the west coast will be very suitable. Right, not solar. What other ones? What about fossil fuel?
That's it. It works everywhere, I think.
Yeah, but what's the problem with fossil fuel?
It's not renewable.
It's not renewable,
Yeah.
is it? But there is an advantage though. What's the advantage?
More efficient.
I wouldn't really say it's more efficient than wind.
Produces more energy.
Yeah, that's one thing. You can get more energy out of it. Yeah, but there's something else that's important.
It's scarce. It's not always around.
Yeah, but what's the good thing about it? No, I'll tell you, okay? So, here's the problem. You have your wind energy on the west coast, alright? So let's imagine that Ireland gets all of its energy from wind. Okay? So what would happen if everybody makes their cup of tea and it's not a windy day?
It's a cold.
It's a cold cup of tea, that's right, yeah. So you can't have all of your energy in one form. It's a mistake. Okay? You need to have things like fossil fuels, so that days when you need more energy, you can use fossil fuel. Okay?
Like a backup.
Like a backup, yeah. So it is wrong to think that you should have all renewable energy. Okay? You should have a lot of renewable energy, but you shouldn't have 100%, because you can see if it's not windy, that's a problem. If there's no sunlight that day, if it's cloudy, that's a problem. Okay? You need to have some backup just in case there's a problem. Yeah? And then there's one other advantage of fossil fuel instead of renewable. And it's cheaper. It's cheaper, yeah. Now when I say cheaper, I mean the total cost. Okay? Because if you think about it, if you want to do this, you're going to have to build new wind turbines. Okay? Whereas a lot of countries already have power plants that can burn fossil fuel. So it's no extra cost if you just buy in more oil and gas. Okay? So when I say cost, I mean the total cost. The cost to make the machine, to repair it, everything. Okay? But as gas becomes more expensive, then this will look more cheaper, a cheaper alternative. Yep? Okay, so on page 84 and 85, there's a lot of information there that you don't really need, but there's diagrams, and these diagrams you don't really need. I just need to give you the idea of what's happening, of changing potential into kinetic, kinetic into electrical. Okay. Let's see. Okay. Yeah, one thing left to do from this. So I'm skipping a couple of pages, but I'm only skipping it because it's just reading that you can do. So if you look at pages here, 90 and 91, you see there they talk about wind energy.
Yeah.
And then the other type, water. So I'll just leave that for you to read if you want to, but I think most people know about this already, wind and water. Yeah? I'm sure it's probably something you would have done in EAP as a reading exercise, right? Renewable energy. No.
And so we talk about coal energy.
Coal, yeah. But if you want, you can read it. But actually, page 92. Do you know what biomass is? Does anyone know this one?
I heard it's like green energy.
Yeah, what exactly?
Yes, good gas.
Biomass. You see biomass there?
Using waste.
Yes, very good. Using waste as energy.
Sweden does that.
Yes, yeah. I don't know which countries are big on it, but basically they use the waste that you throw away. They burn it or they do something with it to make it into energy. Okay. Oh yeah, there's what you were saying, Mohammed, on the bottom of 93, the geothermal. Geothermal. So that's the heat that's under the ground.
That comes from that.
Yeah. And then, yeah, actually, there's the picture on page 94. 94. So you can see they take the heat from the ground. And can you see that? They take the heat from the ground and they push it through the pipes to turn the turbine. Yeah? You can see that in the picture? Yeah. Now, the only reason I'm doing this chapter, really, there's not anything, there's no calculations in it, except for the formula for efficiency, which you will need to use a lot in the exam. Yeah? So there's only one formula from this, which is efficiency. So I'll just give you the questions where you have to use the formula, which are...
It's interesting.
Yes, yeah. What?
No question.
No. Listen, number 2.
We're done with the book.
Number 8. 95. Listen, I'm reading out the question. 2, 8,
96.
Well, we haven't finished T6.
96. Huh?
We haven't finished
I know, so I'm only picking a couple.
28.
Oh yeah, sorry. No, let me be very, very clear. Number 2 and number 8.
Not sorry.
No, that's okay. Also, number 10, because number 10 looks like something I saw in an exam before. Number 10. And one more. I think actually, Yeah, actually go back to the last page, number 5. So we have number 2, number 5, number 8, and number 10.
That's 8 questions.
That's 4 questions.
Plus the,
Oh yeah, but
14.
yeah, that's right. But I'm not going to ask for all of them for tomorrow. Yes. Did you go through during the maths class? Go. Overhydrated, sounds like. Yeah. Okay. Now, tell me, do you want me to do some of the questions from the homework, or do you want to try them? What do you need?
So I didn't explain.
Explanations, yeah. I can have cheeseburger, yeah? What? Yes? Which ones? Explanations we can do some other time. They're boring. Firstly, questions 1 to 5. You wanted to see number 1, and then somebody said another one, didn't they?
That's 5.
5.
I didn't do 5.
It's all explanation, is it?
Yeah.
So could you explain the spring one that is spring?
What do you mean explain the spring
No, I
one?
mean not explain the question 5. It's the equilibrium formula to be used during equilibrium. The X, V, and A.
I do not trust me.
How to find velocity at maximum displacement and
Which one's that?
He's asking for
That one?
It's
What
not,
I
it's not a question, it's just asking for the formula.
Yes.
maximum.
Yeah. For the formulas at maximum.
So you have your formulas for velocity and for acceleration, don't you?
Yeah.
So you just make the cost, you just remove the cost of the sine part. Because the maximum cost can be is 1. The maximum sine can be 1. So if you want the maximum velocity or acceleration or displacement, you basically delete the cost and sine from the formula. And that's it.
So you don't actually have to change sine to cos.
It doesn't actually matter because you're going to remove it anyways, yeah. I think if you try one with that in it, it'll be okay. Do you want to see number 5? Is it?
Yeah.
I mean, I can do whichever ones you want. Number 5. So, soon. Describe an experiment to demonstrate the effects of damping on the oscillatory motion of a vibrating system undergoing free and forced harmonic oscillation. Right. Damping. So, I'm picturing. Now, the nice thing is because they want this to demonstrate the effect, you can really just do something very visual. So this is the experiment I'm picturing. Are you listening? This is the experiment I'm picturing, okay? You have a spring, and you have the ball at the end, and you stretch it down, and it vibrates, and then what happens after a few seconds? It stops. What's the name of this? We say this is damped. Yeah? So what you could do is you could time it. How long it takes to stop. Couldn't you? Yeah?
Doesn't mean damp is like it goes only one way.
No, damp means it's slowing down.
So if it's been down, it's continue.
Yeah, if it's not damped, it should continue without stopping.
Then,
Huh?
or it's not possible.
Not possible. Now, they then say that's the free one, and then part 2, forced. So you could take the same spring, okay, and the same ball, and you can pull it down, okay, except maybe this time you could have some kind of electric motor, the little hammer, you know, they move like this, and you could just have it moving like that. And then you can time how long it takes to stop. Okay? Do you think it'll be faster or slower at the same time? I don't think so. Because I know yesterday I said it's the same, didn't I?
Yeah.
But that is when it's not damped. That's when it's just continuing like this. I think if it's damped, then it does matter. Okay? That when you do this, it will maybe change the time.
Yeah, change the velocity.
Yes, yeah. Because the reason it's damped, the reason it's slowing down is what? Because maybe air friction. Yeah? So if you're shaking it more, do you make more or less air friction?
More.
More. So maybe this makes the time smaller. You know? So how could you check that? Well, spring, release, time it 5 seconds, and then have your little electric motor, the little hammer, and it can vibrate, and then you can time it again. See if it's longer or shorter. Okay? I mean, there's probably many, many ways to do this, okay? But all I want in the question is some way that you can check if it's forced or not forced, if it changes it, okay? Not a lot. So what they're looking for there down soon, what they're looking for there soon is a diagram, 2 diagrams. One with the spring, and then a watch, and then the other diagram, again the spring with the watch, but a little electric motor that's vibrating. And then what could you do? You could turn the motor up higher so it vibrates more, and you can see if it changes it, or vibrate less. So you need to explain that. Okay? This is distracting people, I can see.
As you say,
Yes?
as you say, it's down. Like if it was like only in 1 minute, like in the half an hour,
Yeah.
that's down too, right?
No. What's damped?
So when it's slowed down, like as you say, yeah, I know that.
Yeah.
But like I felt like when it is like a one way, like.
No, just slowing down means damped, that's all. Okay. B. What is the physical origin of the dampening mechanism in the case of the oscillator of a simple pendulum? What the heck does that mean? Well, that means your pendulum, what type of motion is the pendulum?
Oscillation.
Yeah, simple harmonic motion, isn't it?
Yeah.
But is it damped or not damped? It's damped, isn't it? Because will it continue?
Yes. No.
No, eventually what will happen?
It slows down.
Slows down. So their question is what is the reason for this? What is the cause of this? Now, air resistance, air friction. No, I think it's just air resistance, that's all. Is that okay, Dana? Soon. Is that okay, Sue?
Yes.
Yes, okay. Yeah, but the gravity, if you had no air, so if you did this pendulum experiment on the moon, it wouldn't stop. So it's not because of gravity, it's because of the air. You can see this in the videos of the Apollo astronauts on the moon. Okay? What happens is they take their flag and they stick it in the ground, and the flag starts to vibrate. Did you notice video when the astronauts are on the moon, and they put the flag in the moon, and they hit it into the ground. So when you hit a flag into the ground, it vibrates, doesn't it? Yeah? If you watch the video, it doesn't stop. It continues to vibrate. Why does it not stop? There's no air. There's no air to slow it down. So it continues to vibrate. So it looks like the flag is blowing in the wind. But it's not blowing in the wind, because there's no wind. It's just shaking from when they put it into the ground. But it's not damped. So it continues just to shake. Okay? So again, if you did the pendulum on the moon, it should continue for a very long time. Yeah? Yeah. Okay. You don't need to do part 2 or 3 of B in that question. And what about C? Did you do C? C is describe.
Right, yeah.
Discuss actually as you can subsequent.
They just want you to describe what happened. So look, a spring is supported and a mass of 1 kilogram is hung on the lower end and it falls to 5. It's then raised 5 to its original. Okay. Yeah, so can we look up this is what happens. This is 10 centimeters, okay? And then they take, this is not important, is it? This is 10 centimeters, okay? And then they put a weight at the end, and it falls down 5 more centimeters. So what's the total length here? 15. And then somebody lifts the weight up back to 10, and they let go. So if they let go, what happens? It falls down. But it's not at rest because it fell down. Alright? When I click it here, what happens? It slowly drops. But if I then move this back up and then let go, it falls. And because of this, it's like somebody went like this and started shaking. Okay, so it goes, starts at 10, goes to 15, but then goes a little bit more. So maybe to 17. So it will go 17 to 13, 17 to 13.
Until it's done like at 15.
So, yes, you're right. And then eventually it will settle back at 15 because it is damped. And we saw at the start 15 is the rest length. Yes, the equilibrium position. So that's they want you to write a paragraph describing that. So this is, you know, writing. I don't care about that. Yeah. Okay. Oh yeah, it's just writing. Dana Ansun. Wait. Is the only problems for you the description, the writing? Yeah. Yeah. Did you try these? Those four or 5 questions?
Yeah.
Yeah. So what were the problems for you?
5. And you do.
What I was just talking about, yeah. So what exactly was the problem in 5 for you? It's just understanding what they wanted, was it? Yeah. Yeah. Any other problems? I mean, do you want to spend time working on this now? Yeah. And if there's a problem, I can do it on the board. Okay? So 1 and 5 we kind of did. So you should have 2, 3, and 4 done from homework. Are 2, 3, and 4 all calculation?
Yeah.
Yes.
Which you like? You like calculation questions, yeah? So, if you can try to do the rest of those questions. Yes, I'll do it on the board, okay? So in a moment I'll do number 6. If you haven't got number 6 done, can you try it now for me, and then I'll do it. I mean, we should have time, don't we?
Yes, plenty of time.
Plenty of time.
Yeah.
Oh yeah, no worries.
No break.
We'll finish at like 12:40.
30 minutes.
There's loads of time. Yeah, so I'll do some of those on the board.